All right, so today we'll be going through, as I had just said, half of ensemble methods. So ensemble methods actually used to be broken up into multiple topics, and I do think it is worthwhile to go a little bit more in depth into each algorithm rather than doing a very surface level of more of them. So what I'm going to do is do half of ensemble methods today, the other half on Tuesday, and then I'm actually going to combine SVM and pipelines into the same study group, so you don't lose any time. And plus SVM will be a little shorter because it's just one algorithm. Here we're actually going to be talking about two today, 2.5 on Tuesday. So um, yeah, and pipelines is just something that is very procedural with code, so it won't take too much time. Cool. Any questions about that, like minor schedule change? All right, yeah, I think it will be more beneficial to go more in depth into these algorithms as well. All right, if there are no other questions, let's get started. So there are two main kinds of ensemble methods that we'll be talking about, and the two main kinds I'm going to split over the two study groups. So we're going to be talking about bagging methods today, and then boosting methods on Tuesday. So we'll start with bagging, and for this presentation, we'll do a really quick decision tree review. We'll learn about bagging with decision trees, and then also random forests, which is another form of bagging. So as a quick review, these are regression trees. We talked about this just yesterday, so it should be pretty fresh. All you're doing is you're looking for best splits in your data to basically segment your data set into as many non-overlapping sections as possible. And then each segment will end up with a value, which is the average value of all the points, all the training points in that segment. Regression trees are like this, and let's see, classification trees. This is the tree from our example yesterday where we classified irises. Same idea, just instead of a continuous prediction, you basically are seeing which end leaf node has the majority of which class, and that will be your prediction. All right. So visualizing classification and decision trees. One thing that I talked about yesterday as a hyperparameter is tree depth. So this is one way to visualize the depth of a tree. The deeper you get, the more segments you end up with your data. So you can sort of see here we have 4 classes in this random data set. And the more I split, the more granular I can get with my predictions. The more jagged my decision boundaries sort of look on this graph. So for example, here you see this goes straight across, and as you increase depth, the decision boundaries become a little bit more precise. So one thing that I mentioned yesterday as a con of decision trees is that decision trees are extremely prone to overfitting, especially as you get deeper and deeper with your tree depth. So this is an example of that data set earlier. This is an example of what a decision tree could look like. And this just shows with different max depths what your regression line will look like with your data. So here, this is just, imagine this is just all of your data points and all of the X features that you're using. This is your target. If your target is distributed this way, you can sort of see that our max depth 2 line, which is this blue line, doesn't move as much. As compared to our max depth of 5, you can see that it's starting to overfit to specific data points that could be outliers. So that is one thing to look out for in max depth. Again, check for overfitting by comparing your train and test metrics. Questions so far? All right.
Is this a sign function?
This is, I actually do not know what this data is exactly, but it does kind of look like a sign function, yeah. Yeah, I guess it does depend on like what this axis is, but the shape, yeah, the shape is a sign function with a bunch of outliers.
Okay, thank you.
You're welcome. All right, so I recap decision trees just because the algorithms that we'll be talking about today also involve decision trees. So what we've learned is that, trees are pretty great, right? I think we can all agree that trees are pretty great. So really quick overview of decision trees. Again, works well with nonlinear relationships. right before I started the recording, Adina had asked the question about with your dummy variables, you actually don't have to do a drop first equals to true for these nonlinear models, because drop first equals to true, we use that in our linear regression to combat multicollinearity. And that is not something that we have to deal with these models. Decision trees are also pretty easy to interpret. It does implicit feature selection, because if your data doesn't split nicely across certain features, it won't even, it knows not to learn that. Also accounts for interaction. The main disadvantage, again, it tends to overfit, especially if their end nodes end up being completely pure. And small changes in the input data can cause large changes to the structure of the tree. So you can imagine, like, you build a tree, you do a train test split with your training data. Perhaps like the first split it comes up with is, I don't know, split A. If you were to do cross-validation, very, very likely your trees will end up completely different, just because with different subsets of data, it finds different best splits. So that is one very, very big disadvantage of decision trees. One, they overfit, and also they're extremely unstable. Minor changes to your data set and different distributions of your subsets of your data can cause large changes to the structure of the tree. Because once your first split is different, you can imagine all your ongoing splits, subsequent splits, I mean, will be different. Any questions about this before we move on to ensemble methods? All right. So I don't know if anyone's heard of the phrase, the wisdom of the crowd. So the idea of wisdom of the crowd is basically what ensemble methods are built off of. So wisdom of the crowd basically comes from this experiment, you know, those like fair games where you try and guess like the weight of like a giant fruit, or like in this case, the weight of an ox, or like count the number of jelly beans in a jar. They say that wisdom of the crowd tends to produce better results than individual guessing. So here, with this specific example, this statistician found that when 800 people guessed how much this ox weighed, it turns out that the actual weight was only 1% off from the median guess. So what they're saying is an aggregation of a bunch of people's random guesses tends to be better than just one person making an educated guess. So that's the whole idea of, that's basically what the idea of what ensemble methods are based off of. Just the aggregation of many people's guesses versus being better than just one person's guess. So the takeaway is that you can learn a lot by combining different learners. And this is called an ensemble method. Any method that combines more than one model is known as an ensemble method. So in essence, we can combine the output of models that are not accurate enough on their own to get wisdom from the crowd. In this case, I love that they stick with like the semantics of trees. With decision trees, you can actually sort of grow forests of trees. So we're going to talk about two main tree ensemble methods today, one of which is bagged trees, and then we're also going to talk about random forests. People often get confused between the two, but they are two different algorithms. So there's bagged trees and then random forests. So first, bagged trees. This is just like an overview of the steps that we're going to go into more detail with in a little bit. But first, what we're going to do is we're going to bootstrap this data set. And I'll talk about the process of bootstrapping later. Next, we're going to build a tree using a bootstrap data set. And you're just going to repeat these many, many times and aggregate all these trees. You're going to output the prediction through each tree that you build. And for classification, take the majority predicted value. And for regression, take the average of the prediction. So the idea of bootstrapping, and we'll get into that process in a little bit, is you're going to end up building trees using different subsets of your data set, of your main training data set. So you do end up with different looking trees that you can then aggregate and sort of take the average of. Questions about this process so far? All right, so bootstrapping. So because trees are prone to overfitting, and it's because they have a high variance, especially when they are built to full purity in each leaf, bootstrapping is the process of switching up our data set such that you're accounting for different patterns within your data. So what bootstrapping is you're going to take samples with replacement from your training data to create bootstrap samples that are of the same size. So in this case, we have an n equals to 9 sample here. And each of these are bootstrapped data sets from this training original sample. So how you create these is you're sampling with replacement. So each data point here has an equal probability of being chosen at each step. So what you're doing here for this first example, your first point that you pick is a blue point, you put it back, you're going to pick another one, turns out it's another blue point, you put it back, blue again, and then you're just going to repeat it until you have created a data set that is the same size as your original data set. So what this does is it essentially sort of changes the distribution of your data a little bit, but all of the data does come from your original data set. And this is the process of bootstrapping. Questions about this? I do have another example with data that does make more sense after this. Cool. So this is like a data frame example. So here, this is a heart disease data set, and here you can see this is our target. Our original data set, this is just a snapshot of it. This will be our first 4 rows. And you can see here in our bootstrap data set, because we're sampling with replacement, you actually can end up with the same data point being chosen multiple times. So this is just an example of a bootstrap data set that is bootstrapped from this data set. So all you're doing is you're just sampling with replacement data points from your train set to just create these other bootstrap data sets. And you can imagine that the trees that you build as a result of these bootstrap data sets might look different because some points won't be considered, some will be considered multiple times. And those minor changes in the distribution of your data can help combat overfitting because you're introducing a little bit of randomness there. All right, so bootstrapping followed by aggregating. So like I mentioned, once you have taken all the bootstrap samples, you fit a decision tree for each sample. So each tree, again, will have a low bias and high variance, very, very prone to overfitting, each tree. However, you repeat this many, many times, all your trees will be slightly different, and you might get different classification results by running your test data through each tree. So you're feeding your data through all of the bootstrap trees. And then again, for classification, you just take whichever class is predicted most by your bootstrap decision trees. Perhaps you train like 100 decision trees and just see like maybe out of your 2 classes, you get 56 of your trees predicting class 0, 44 predicting class 1. So your overall prediction will be class 0. You can also do the same for regression by just taking the average of the predicted values. Questions about this? Cool. Just to go a little bit more into aggregating, you can actually decide on how you want to vote, how you want your trees to vote. So imagine you have these 3 trees here. You just take their output, see which one is predicted the most number of times, and you can get your final classification result. There are other forms of voting, so you can also weight each model, weight each individual tree by their overall like accuracy metric. That's also something that you can define in the bagged trees algorithm, just so you all know. All right, so bootstrapping plus aggregating, that's where we get the term bagging from. So bagging, any bagging algorithm is something that includes a bootstrapping step and an aggregating step. And bagged trees is one of the more straightforward bagging algorithms. So if we just take a look at the decision boundary for a single decision tree versus decision trees with bagging, you sort of see a much smoother, less overfit decision boundary when you have bagging. Just because you're considering more models, you have a bunch of weak learners working together, and you end up with this averaged prediction. So therefore, again, another example of how the Ensemble method prevents overfitting. And yeah, questions about this? Cool. So you can imagine it would be kind of inefficient to just build a bunch of trees and test each one like, when we build a model, I always like to say, always check your evaluation metrics. Can imagine this process if you're building 100 trees and you're doing like this cross-validation, or you're doing like a bunch of different train test splits and testing your model, can get pretty inefficient. So therefore, there's this other, there's this kind of embedded way of doing cross-validation called the out-of-bag error. So the out-of-bag error basically means that you can sort of think of it as your train test split within your train test split. In general, on each decision tree, only 2/3 of the observation will be trained with each model. So for each model, only 2/3 and a random 2/3 of your bootstrap data set will be trained with each model. So again, as I just mentioned, cross-validation on bagged classifiers or regressors is going to be challenging because it can be very computationally expensive. Because if you remember cross-validation, literally whatever your cross-validation number is, you're dividing your data set into that many parts and retraining your model that number of times. So if you're doing 100 trees and you're doing another cross-validation step of like a CV equals to 5, you're going to end up training and testing 500 trees in total. So just by doing this out-of-bag error, you're doing a train test split for each tree, and that's much faster than doing like the cross-validation. So all you have to do is look at every observation and then make a prediction for each of the data points for which the data points wasn't used to create the tree. So for the 1/3 of the points that weren't used to create the tree, you're just going to do a quick test using those 1/3, and that's where your evaluation metric for each individual tree comes from. So it's sort of like doing a train test split within your train set for each tree, which is much more efficient than doing cross-validation. And this is known as the out-of-bag, checking for the out-of-bag error. So essentially, it's just another level of cross-validation, just not as in-depth, and you aren't retraining your model as many times. Cool. Any questions so far? All right, so the issue with bagging. So bagging does sound like, it combats the overfitting problem of your decision trees pretty well. The issue is that trees might be correlated with each other, and that just leaves some trees to be kind of redundant. So there might be a feature that's very, very powerful in generating a separation boundary between different categories, which results in trees that are correlated to one another despite being for bootstrap samples. What that means is, one way to think about it is, let's say you have this one feature that has a very clear decision boundary that the tree can create. So no matter how you bootstrap your data set, that feature will always be there. And therefore, for example, maybe like the first 2 splits that's created in your data are exactly the same. Then what's the point of doing all of this bootstrapping and aggregating when all your trees end up looking very similar? So that is the issue with bagging. Does the idea of like correlated trees, does anyone need clarification in that? Cool. So we just need to do something to ensure that bootstrap samples aren't correlated with each other. Did I hear someone kind of start asking a question? Not sure.
Yeah, I have a question. It's because of the information gain of the trees that we have this problem.
Yeah, exactly. So sometimes like you might have a feature that no matter how you bootstrap your data set, even though you're taking like samples with replacement, maybe the same feature still provides the most information gain. And so, yeah, that's how you end up with this correlated trees issue.
Okay, thank you.
You're welcome. So this leads us into our next algorithm, which is random forests. And remember again that random forests and bag trees very similar, but there is an added feature of randomness in random forests that makes it different from bag trees. So random forest recipe, very, very similar. So what we're doing, same thing, we're going to bootstrap the data set again. The new step here is you're going to build a tree using only a random subset of features at each node from this bootstrap data set. So what that means is every time, before you split your tree, you're going to first only take a subset of features, and the subset of features is actually quite a small number in relation to the total number of features, and I'll get into that later on as well, you're going to only consider like a fraction of your features at each split. So literally, let's say you have 10 features. At your first split, you're maybe only going to consider feature like 2, 4, 6. And at your next split, maybe you only consider features like 1, 3, and 5. So at each split, different features are going to be considered. And so you can imagine, because of this added randomness, your trees will end up looking much more different compared to the bagged trees. So again, you're going to repeat these steps over and over again per each tree you want in your random forest algorithm, aggregate them, and the prediction done the same way. Regression, you take an average, and for classification, take the majority. Questions about this?
We still have our out-of-bag
Yes,
data?
out of bag is also used in this in exactly the same way with bag trees.
So they have the full number of features in them, right?
Yes.
So the size of them would be different?
The size? So
I mean the shape.
Yeah. The shape of your data frame, you mean?
The shape of out-of-bag and these data that we use for each trees. For example, out-of-bags have 10 features, and these data would have 3 features.
Yeah, that's a really great clarification.
How we calculate the errors, I mean?
Yeah, so let's say, you have 10 features, and yes, it's true that each of these trees at each split is going to only consider like a subset of features at each split. But when you're taking your full data and running it through each random forest tree, you still need to consider all the features, because you don't know, even though you have 10 features and at each split you're considering a different 3 features, for example, all 10 features will probably come into play at some point in the tree. So it's only in the way the tree is being built that you're only considering certain features at each split. But overall, the data that goes into your tree should still contain all the features.
Okay, I got it.
Okay, awesome. Cool. So here you can sort of see this is the same Bootstrap data set that we had from before. I believe this is like 2, 1, 4, and 4. So same idea of bootstrapping as we had before, but now we're only going to consider, let's say, 2 out of these 4 variables to create our splits. And that's the main difference between random forest and bagged trees. So let's take a look and see. Random forests basically decorrelate each decision tree created in bagging by ensuring that at each split only M features are considered. And the default is actually M being the square root of your total number of features. So if I had 10 features, square root of 10 is like maybe like around 3, a little bit over 3. So out of 10 features, you're only going to consider 3 of your features at each split. And as I mentioned, the number of features you consider is usually a minority number. So that means that on average, that number of splits won't be considered given a strong predictor. So as we increase the number of trees, this will lead to even less overfitting. You can sort of think of it as, remember how with bag trees, you end up with a smoothing of the decision boundary? This process will smooth it out even more, because you're introducing this randomness. You're forcing your trees to consider factors that it might just discount in a regular decision tree. So what you do here, even if you're increasing the number of trees, it doesn't lead to overfitting. So you should make as many trees as possible until you achieve an acceptable error rate. And usually what you do with this is you plot a graph that looks just like this one. You can plot here the out-of-bag error rate. You can also plot the overall model accuracy. That's also something you can plot. And what you'll see is typically like a plateauing of your error as you increase your estimators. So here basically refers to the number of trees in your forest. And as you increase the number of trees in your forest, your error rate will start to plateau at some point. Now, these three different lines are just a different values for your hyperparameter of max features. So you can see here by default, it is the square root, which here looks like it gives you the lowest out of bag error, but other other values you can tune for this hyperparameter include the log base 2 of the number of features, and this is none. Max features equals to none, which means that I believe max features equal to none means that you consider every feature. And you can see here, this one still ends up with a higher error. And this is, I think, because out of bag error rate is sort of like your test data. Maybe you could check your in bag versus out of bag error rate. I have a feeling this might be due to overfitting. So questions about this? I feel like I'm like giving a lot of new information, and I understand it's a lot. This is one algorithm that you definitely want to take some time and like sit down with to just like remember all the steps of what's going on.
Just a quick thought, can you also randomize the number of M features that is selected at each point? Is that like the method that they use, or is it always the same?
That's a good question. I'm not super sure. Let's see if it allows you to give like something random. So here it looks like it's not one of the options that you can use here. There are actually a lot of other different kind of forest algorithms. So I'm not sure if you can find a list here. Scikit-learn forest. There are basically a lot of different kinds of forest algorithms. Let's see if they have this here. Yeah, there's extra trees classifier, which are extra random trees, and it works slightly different. I forget how exactly that adds a level of randomness, but yeah, other tree methods exist. Other tree ensemble methods exist. That I think some of them, I'm not sure if that's the way they randomize it, but there are other big models that do the randomizing differently that might give you different, better, or worse results. But yeah, that's a good thought. But in random forest, this is not something that changes with each tree or with each node. Cool. Anything else? All right. So the random subspace sampling method, which is, the randomly choosing features at each node. One thing to remember is the features are randomly chosen at each node and not for the entire decision tree. So again, with the 10 features at each node, it can be a different subset being considered. So your tree is not just built on 3 features, it is still built on 10. And yes, this is just to ensure our trees are decorrelated and that they have diverse opinions. So this is just an output of, I forget where this is from. I believe this might be from the ISLR textbook that I sent out. But this is just comparing the results of bagging and random forests. And here you can see our test metrics are this black line and this orange line over here. And this is our error, so the lower the better. Our random forest tends to converge and do better than bagging, just because of that added that added layer of randomness in the features it's considering. And yeah, this is these two are the out of bag error. Cool. So just as an overall advantages and disadvantages of your random forests, pros, it's very, very powerful. It nearly always outperforms decision trees because it prevents that overfitting. It is able to detect nonlinear relationships very well. Again, because you're considering a different subset of features at each time, it's going to look for splits across different dimensions. And harder than other models to overfit. As we saw with a lot of these error graphs, the test error tends to, the train and test errors actually both tend to plateau at some point. So it's pretty easy to select the number of trees in your model. Disadvantages, it is less interpretable. It's very hard to say, all right, what was the first feature that was being split, because you are aggregating the result from multiple trees. If you remember, for decision trees, you can output the graphic of the tree. Interestingly, not many people do this, but you can. If you want to, you can actually output it in the same way. And I believe they actually give you, if you have like 100 trees in your random forest, you can actually print as a GIF all 100 trees, and it'll just like flash through the 100 trees in your model, which I don't know why. I don't think you can get much information from that, but it's a cool thing that you can output using that same library. Another disadvantage is that there are many, many hyperparameters to tune. So therefore, grid search is your friend. Grid search is something that is in this topic. I am not going to talk about it. I guess if we do have time, I can talk about it today. I was planning to talk about it on Tuesday, but yeah, depending on time, we might get into grid search, because grid search might be very useful. It is going to be very useful for your projects. But grid search is basically a library within scikit-learn that allows you to pick your hyperparameters much more efficiently. But yeah, any other questions? I'm going to actually get into some of these hyperparameters. All right. So some of the main hyperparameters that you can tune in your random forest, and a lot of these are actually similar to the hyperparameters in bagged trees. So just so you know. End estimators is the number of trees that you want in your forest. This is something that, again, you can plot the error graph to see where your error value starts to plateau. And you would basically choose the starting point before it starts to plateau, because why add more trees when they don't have a marginal increase in your error values or decrease in your error values? The criterion is exactly the same as your decision tree, because it is made of a bunch of decision trees, Gini or entropy. And for this one, whichever one you choose, each tree will be built with the same criterion. I don't think that there is a method to like randomly say like some trees with Gini, some trees with entropy. You can also do max features, which is one I mentioned earlier. By default, it's the square root of the number of columns that you have, but you can also tune this. You can actually also give it an integer if you'd like. Max depth, again, in decision trees, this is the parameter that leads to overfitting. But because of the subsetting of features, max depth being very, very large, if you have a deeper tree, because you have many trees being aggregated at the same time, max depth in this case won't lead to overfitting as much. You just have more granularity in your classification. Finally, you can also set bootstrap equals to true or not. Out of bag score, that's something that you can get as well. And end jobs, actually pretty interesting. Some of, I'd say like this section and next section, this topic and next topics models, because they do take up a lot of computing power. End jobs is something you can tune to tell your model to tell your computer how many cores you want to use when training your trees. I do not know anything about cores, but I know they, I think, come in like 4, 6, and 8, maybe. I'm not too sure. But one that people usually set is if you set end jobs equals to -1, it uses all of your cores, which may or may not be good for your computer. I honestly am not too sure. I don't know much about hardware, but if you do know, this is something you can tune as well. Questions about any of these hyperparameters? Awesome. So something else that's really neat about tree methods is you can extract feature importances. So feature importances is basically a way that you can do your feature level analysis. So whereas in linear regression, we did like a coefficient level analysis to see like, all right, well, you increase this feature by how much, your target will increase by how much. You don't have that exact sort of relationship for these tree models, but you can sort of see which features are contributing most to your classification. And so, for example, this is in our iris data set. The petal width and petal length seem to be more important than sepal width and length. And so basically what it does is it trains the random forest. By doing this feature importance, it looks at the relative performance of your model with and without one feature, and just take a look and see how much better, how much worse a model will do without that feature. So basically, if this has a large feature importance, meaning that if we don't consider petal width your model will do much worse compared to if you were to get rid of sepal length. I don't know if that made sense. So there are two main ways to determine feature importance, and that's just one of them. The other one, honestly, I don't remember off the top of my head, but I will send something out for you all that explains it. So I would say that if your final model is a random forest or bag trees or decision trees, any tree-based method, you can actually get this graph. Actually, you can sort of see it here. Let me go back to our random forest classifier. After you fit your model, you can actually extract all of the information from feature importances. So all you have to do is do model.featureimportances. It will give you the scores, and all you have to do is just like match it back to your feature names, and it does it in the same order as your input data. So all you have to do is just like zip it together. Maybe you plot a graph. And so that's how you can get that information. If you choose your final model to be one of these, I definitely want to see a feature importances graph so you can in some way maybe interpret your model. Maybe for your project, you can say this feature contributes most to like this kind of classification, so on and so forth. So that's going to be one that I think a lot of you will end up using. Any questions about this? All right. So on another note, you can actually create custom ensemble methods. Within scikit-learn, there is a voting classifier or voting regressor model that you can actually use. And it's pretty cool. Let me actually pull up the documentation real quick. Voting classifier. So with your voting classifier, you can see here that one of the parameters is a list of your tuples of your estimators. So basically what it will do is, for example, you want to try out aggregating your KNN, your logistic regression, and like a decision tree. So what you do is you give it tuples of like, you have to name it as well. So you'll be like KNN, comma, and then your instantiated model. What that will do is your data will go through all three models, and you'll basically have a voting classifier based on what each individual model outputs. It'll aggregate that information and give you an overall output. So again, I talked about the different voting. So majority rule voting, and this is also, you also have soft voting, which is more of a weighted probability, a weighted average classifier. So just based on the probability values, because a lot of models will be able to output like a probability of being class 0 versus class 1. So that's how they do the soft voting. I will say not every model you'll be able to use this. So if you do run into an error here, and if you do decide to use this and you run into an error there, that could be why. But yeah, voting classifier could be something interesting to look at. This is the idea of not model stacking. Model stacking I'll talk about another time. But yeah, this is a way that you can aggregate a bunch of the models that you already know if you want to use all of them in one single model. Questions about that? Cool. Well, that is all I had to talk about for bagging methods. I'll probably pull up grid search, because grid search, I really only want to just talk about the syntax real quick. So I'll do that right now. On Tuesday, we'll talk about boosting algorithms. So if you get to those lessons, feel free to go through them, but I will talk about them in study group on Tuesday. So since we're here, I actually have to pull it up from, let me just pull it up in Canvas. I want to talk about grid search. So grid search, as I mentioned, is a very, very efficient way, or not time efficient, but code efficient. It's a code efficient way of deciding on your hyperparameters. So let me pull up, let's see, let's just do it with this lab. Oh, let me take a look at the chat as well. All right. So just looking at the chat, cool. Nebraska, you weigh cows as a pastime. That's cool. And Matthew had a question on when you bootstrap, do you always keep the original amount as the sample size? Typically, yes. When you bootstrap, you do keep the original amount as the sample size. I'm not 100% sure that is something you can tune, but most of the time when you're bootstrapping, you're using the same sample size number. Cool. So grid search, it's really getting used to the syntax, I think, but grid search is something that will be very, very helpful as you get to tuning your hyperparameters. So not bootstrapping, grid search will work for any algorithm that has hyperparameters to tune. So the way that it works, and let me actually get the solutions up so I can walk through the code. With grid search, you want to actually start by first instantiating a model. So in this example, or actually, let me see. Yeah, in this example, we're going to do grid search over a decision tree classifier. And what that means is we're just going to do grid search to figure out the best combination of hyperparameters for this decision tree on this training data. So it basically stops you, it prevents you from having to tune each one separately, like, doing the graph of like max depth, or like just testing random values of like, your two criteria, like your Gini or entropy, or doing, what's the other one, like a min sample split. These are all different values that you can, you would end up running a bunch, like maybe 10 plus models if you wanted to tune all of those things. Grid search simplifies that process. So here you can see just a single decision tree classifier. I think this is the vanilla one, has an overall cross-validation score of 56% or 57%. Let's just see how grid search can help with that. With grid search, the first step you have to do is come up with your parameter grid. And so the way the parameter grid is set up, you can see that this is a dictionary with the keys corresponding to the parameters that you want to tune. And each key points to a list of values that you want to test for each hyperparameter. Let me zoom in a little bit so it's a little clearer. There we go. So this is decision tree. This can be whatever you want to call it. This is just decision tree parameter grid. So you can see here, you have our two criteria, our two cost functions. We have different depths, so they're going to test max depth and also trees of 2, 3, 4, 5, 6. Number of minimum samples before you can make a split, and the minimum samples you can have in your leaf. So, all right, imagine with this grid of parameters, how many models are you going to end up running? So with grid search, it's going to test every single combination of parameters that you give it in your grid. So here you can see there's 2 times 6 times 3 times 6. So that's like what, 36, 72 times 3, 216? Yeah, over 200 models are going to be run with all these different parameters, and it's going to basically give you the best combination of hyperparameters. But you imagine you want to be a little bit smart about this. Maybe don't test 200 different models at the start. Usually what I like to do is maybe like perhaps test like for max depth, maybe I try like 1, 2, 3 first. If it chooses 3, then maybe I test like 3, 4, things like that. So you can narrow it down so you're not running that many. But yeah, it looks like you end up having to search through 648 different trees, again, because this is doing cross-validation. So let me get to that part as well. So the way that you do grid search is you have to import your grid search CV. CV stands for cross-validation. You have your classifier, which you have instantiated at the top. You have your parameter grid, which is that dictionary of all your values that you want to test out. How many folds of cross-validation? The more you do, the more number, like you multiply the number of times your model is going to run by that number. So if that number is bigger, you're going to run way many more models. It's going to take very long. And then you can also return your score. So here, all you do is very similar to like a plain model. You can call .fit on your grid search. And after you do that, and these are all your parameters that you're giving it, you can actually take a look at your grid search score. So your best score, your mean train score being 67.81, best test score being 56. That's the average of all of the models, which I don't think is as relevant here, but you can also get your best parameter combination. That's the main point of grid search. You don't have to run your model over and over again. You don't have to keep pressing Shift Enter to run a model. It does it all at once, and then you can spit out using the best params attribute. This is what you get. So as your final model, you can just plug in these results and then do the rest from there. So let's see if there's anything else. Does anyone have any questions about grid search? Well, definitely something worth trying in your mini project, because you're definitely going to want to do grid search for your final project, especially for like whatever model you're going to fine tune. So yeah, let's see. Yeah, in this, I think this is a pretty good lab to just go through to get used to running grid search. Just be careful that if you put too many parameters, it will take a very, very long time to run. So just be aware of that. I know some students have actually set up grid search with a lot of parameters to run overnight. That's definitely something you can think of doing. But if it is, because one thing with grid search is it's saving all of your trees and it's saving all of your parameter values. It does get quite memory intensive. So when you max out your memory, your kernel will die and you'll lose all of your results. So be careful about that. That's why you don't want to test too many parameters at once, but it still makes the process overall, I think, a little bit more efficient. So yeah, this lab just goes through another example using random forest, and it's exactly the same. So you can see here, they fit the grid search. This one is going to take a while, and then you end up with your optimal parameters here. There we go. So yeah, I think, yeah, I just really wanted to talk about the syntax of grid search. If anyone has any other questions on that, I'm happy to talk about it more on Tuesday if needed, but I think following the labs, it should be pretty straightforward. Cool. Any other questions regarding today's material, or actually any other material that we've gone through so far?
Just quick question on the computation. So I was reading with boosting, each model's done like consecutively one after the other because it depends on the previous. And random forest, they compute all the models at once. So does that mean boosting has a higher computation cost, or is it hard to compare?
In terms of, so you measure efficiency in terms of memory and also in terms of speed. So in terms of memory, I would say that they're pretty comparable. Again, depends on like the underlying algorithm. So in terms of memory, pretty comparable because they're saving the same information. But in terms of speed, yes, you're absolutely right. You'll see in most results when you compare the time taken to train a model, boosting models take much longer than bagging models, even though they are both ensemble methods. And exactly, I think it does have something to do with like the n cores parameter, because that basically allows you to run things simultaneously. Again, I'm not familiar with hardware, but I've been told that that has something to do with it. Cool. Any other questions? All right, the one thing that I realized I forgot to tell you all about the mini project, we are actually I'm going to kick off our third project next Thursday. So this coming Thursday. So best to have the mini project done by then. So at least I can look it over and give you feedback on your processes. The main thing I'm looking out for in the mini project is really just the process of implementing your model and evaluating its results. Some of you have asked me questions about the data itself. Data set is not great. A lot of missing values, a lot of zero values when there shouldn't be. So for those of you who haven't started, just keep that in mind. I don't need to see like in-depth feature analysis for this one. I think as long as you have data clean, the main thing I want you all to have practice with is just training the models and also your classification metrics. So like your confusion matrix and your like accuracy F1 precision recall. So those are the two things I'm going to be looking at for the mini projects. If you have like weird coefficients, if you have like, if you didn't deal with your imbalance data, that is fine. That's something that you can save for your actual project. There's one more thing I wanted to say regarding that. Oh, the mini project is also a very, very good opportunity to start thinking of how you can functionalize your modeling process. So you will be printing out the metrics for all of your models that you're going to run. highly recommend just creating a function that does all your metrics at once. So you don't have to individually print out like your accuracy, so on and so forth with your confusion matrix in separate outputs. You can highly recommend you all try to create a function that does it all at once. And how you want to do that is really up to you. When we get closer to the project, I'll show some examples of how you could do that, but do not copy that code because I will know. So yeah, that's regarding the mini project. Would love to see it before I kick off the project on Thursday. Even if you don't run all the models, I think it is worthwhile to just like, if you want to just check the process of your modeling, I'm more than happy to look over that. So yeah. Any other questions regarding that?
Hey, Ish, can you say the 2 things that you were going to be looking for in the mini project? I'm sorry, I didn't get a chance to note those.
No worries. So the two main things I'm looking out for is the modeling process, like you're fitting the model and like getting your predictions, as well as evaluating your model. So your evaluation metrics. You should have a confusion matrix and your accuracy, F1, recall, precision for each model that you run. So those are the 2 main things I'm looking out for.
Thank you.
And also on some other level, if you do end up using like a scalar to transform your data, I'll just check to make sure that you're doing that in the right place. So yeah.
Okay.
Cool. Anything else? All right. Well, let me stop this recording because today is Friday. Where is the recording stop button?